I'm a little bit more blonde than that, but I don't look like a dune and I don't look like a hand, so that's good. So excited to be here. This is awesome. I've only had the opportunity to watch the videos before, and they just don't compare to being here. This is really incredible. The organizers and MCs are awesome. Let's hear it for them real quick. Like, really incredible. I'm excited to talk to you about something probably a little different than most of the other presentations today, which I always like being able to do that. First up, I'm Andrew. I work at a company called Textile. You can find me on Twitter. You can find our company, learn a bit about us. I'll only touch a little bit on things that we do towards the end because I want to talk to you about something pretty big and interesting. Coming to an event like this is really neat because we write TypeScript and JavaScript all day long, and we use React a lot, and the companies that we work with use React all over the place. But we don't work on React directly, and so it's almost like I'm on a different celestial body. And so I think that I have a lot of really cool things to share with you and a lot of interesting perspectives for you to take back to your own projects and think about how we can do things differently on the web and build a better internet. But to kind of ground it in some ideas, I just wanted to actually talk about some really simple apps that for some reason keep crossing my mind, and the challenges to doing them in just simple ways. And so, has anybody played Werewolf? Yes, that would have been my response too, exactly. So Werewolf, it's a card game. You don't really even need the cards, but you take 7 people, there's 1 organizer, there's 2 wolves, everybody's a villager, and there's night and day, and people have to figure out who the wolves are and kill them before they kill all the villagers. I was just at home with all my family, and every time I'm with my sister, she has one of these decks of cards, and we go, oh, we should play Werewolf. But the problem is that you need 7 people. You need this organizer, and her daughters are too young to be the organizer. And so we always hit this weird snag, and it's always like 6 people. And we're like, oh, how do we do it? One time we tried to play with like bamboo poles where you'd have to close your eyes and poke people, which just turned into a totally different game. And so I wonder, like, okay, what would it take just to build a really simple app? I mean, there's like just the most basic logic here to building a game like that. And so, if you wanted to create this, you'd build your app and you'd run it in, on your laptop, or people could have their phones and pull up the app, and it would reveal to them what their role was, and then it would go through the series of the sequence of events in the game until it was over, and it'd be, more or less straightforward. But the way that we build apps today creates some problems with this. So my family lives in the middle of nowhere where we rarely have cell phone connection, and oftentimes the internet isn't great. But building an app like that, it means it can't run without a great connection, because every time that the app needs to move forward, every time there's a state change in that application, it needs to go back to the server that's going to actually orchestrate what all the different players are seeing and doing. So it can't run locally, and if the internet breaks or the connection breaks, the app breaks. And that's really weird for such a simple application, why it has to be that way. Why these apps can't actually just talk directly to each other. And a lot of you have probably tried to go through the steps, at least, of building applications that do speak directly to one another, building peer-to-peer applications, but you've probably hit a lot of snags along the way, and you've realized, wow, this isn't quite the way that the internet seems to be designed. Okay, another application that for some reason I keep thinking about is like, I really just want a good news feed. Who wants a good news feed, right? And so, maybe it's something like RSS and your personal RSS feeds, but you also want that algorithm to just go and find you the things that you're missing. So you want a news feed that's from reputable sources. It's unfiltered, it's uncensored, it's unaltered, it's real time. Why doesn't that exist? And even if it did exist, how are you sure that it's going to be able to continue existing in the world? Okay, so you go about building that application in the normal approach, and you have some big server that sits out on the cloud, and it's going to present this feed to all of its users. And it's not even the responsibility of just that server. It's all the nodes of servers in between that server and the end user that can actually do things to change the way this app runs. And we see that in the world today. The internet isn't actually wide open and just used the way that people want to use it. There are people tampering with it all the time. And there's a lot of reasons beyond tampering why a setup like this might fail. And with things like the news and your understanding of the world around you, having those points of failure can be really important and detrimental. right? And so there's just, not only can you get bad things, people can tamper with it, it's introducing some places where this is just a suboptimal setup. It's going to be slower. It's going to be not good for its users. Of course, there are some times and some ways that this is actually just a lot better, too. Okay, another one. I recently had an MRI on my knee. All good. I'm standing here, but I went to get the MRI like on a Tuesday. They handed me a CD at the end of it. It's the first time I've seen a CD in like 10 years. I took the CD and I went to the doctor's like a week later. He took the CD, he put it on his laptop. He pulled up this archaic software, flipping through it and making his laptop sort of freeze every once in a while. So we were laughing about the state of healthcare applications being so like old and archaic. And I was wondering, why can't I just collect my own records? Oh, even more than that, a woman in front of me in line checking into the doctor had forgotten her CD. And so they said, oh, we can't actually help you. You're going to have to come back a week later. You're going to have to make a new appointment and come back a week later. So why can't we just collect our health records, have them on our devices, move them around with us, actually provide access control to the doctors as we're seeing them, show them on their laptop, take that control back. For some reason, a doctor's office for me is always that place that I don't have cell phone connection. It's like maybe it's too many Faraday cages, maybe it's not enough Faraday cages. For some reason, it doesn't work, so we need other ways to make that happen. I don't really think that I want the full scan of my knee on my mobile device, so I need other ways to control and interact with data. So once again, we have this suboptimal setup, so it makes building apps like that a little bit challenging, and it makes things like owning our personal data kind of costly, and it makes it hard for applications to build good infrastructures to do that, be able to get things like GDPR compliance. It also means that a lot of the APIs that you build, no matter how good your intentions are in building them, you've created lock-in, you've created a dependency on them where people don't actually own the things that they're putting behind those APIs. And of course, it always relies on the infrastructure, the internet, how we built it, working really, really well. And a lot of the infrastructure of the internet, how we've built it, is more or less optimized for Web 2.0. And I'll go more in depth into that as we go forward. But imagine I want to just share with you this GIF, right? Or GIF. I want to get this to you. I made everybody happy or everybody mad, I don't know. But I want to get this to you, and so I give you the URL. That URL doesn't work, so don't try it. So you're all going to go and you're going to request it from the server, and then you're going to all wait for that request to come back to you. And along the way, it's going to pass through dozens or hundreds, or with this group, thousands of different servers all passing it forward. But we're all in the same room. That's the way that we've set this up. And so imagine that now with Netflix videos in your household and the households next to you, and thinking through how we're actually doing content delivery. And there's just really weird setups of the internet that we all just take as the default. And there are other ways to do it. And not only are we taking it as the default, it's actually created this virtuous cycle or unvirtuous cycle where we're creating more centralization of the internet. We're creating latency and suboptimal setups where they don't need to be. We're forcing applications to be online first. We're making data inoperable, interoperable, non-interoperable. And we're using data often that's unverified. We're not sure if it's the same source data. How does my doctor know that they're looking at the same record that I'm looking at on my phone? And so IPFS, I'm going to talk about it in a few different ways, and I'm going to try to pin it to things on the ground today. But the idea behind this project is to try to solve a lot of these really big problems and take our internet to the next place, to make it really, really strong and resilient in the future. And so let's talk about IPFS. How many people in the room have used IPFS before? How many people in the room have heard of IPFS before? Awesome. How many people in the room want to know what IPFS stands for? Okay, cool. I will get you that far in this talk at least. So I'm going to tell you kind of three big ideas behind IPFS, and then I'm going to talk about a few of the fundamental ways that it works, and then I'm going to tell you some ways that you can connect it to the apps that you're building in some interesting ways. So IPFS has one of the coolest names. It stands for the Interplanetary File System. The there's a lot of ways to interpret that, but actually, if you even want to interpret it literally, it's a pretty interesting exercise. Imagine that we do make it to Mars, and imagine actually setting up an internet that works, that can work across a 30, 40-minute round trip ping request. So we need different architectures for those sorts of setups, but there's a lot of other really interesting meaning that is layered behind that name. So IPFS is a trustless, self-organizing network that's meant as an alternative to HTTP, but really works to augment HTTP and be used as an alternative and alongside of HTTP where it matters and where it can present itself really useful for the use cases that we're building towards. Self-organized is super, super interesting. So imagining that you can actually speak as a network here between all the participants of this network without having to go off necessarily to different nodes also allows us to self-organize a network if we're disconnected from those external nodes. And so that means that you can build, there's maybe 100 different examples of chat apps that are built on IPFS all the time that then allow you to do real-time local chat without connections to the external world. So that's about the network a bit. About the structure of how data is organized and moved in IPFS is really neat because it actually has some internal opinions about how data should be, and what that sort of leads to is this idea that all of the world's data can be organized as an interlinked tree, which is really cool. And you don't have to use it that way. You don't have to really think about your data fitting into the world that way. But when you start thinking about that, you can imagine the idea of owning your entire computing system all by the hash of the root of that data. And we can think of totally different architectures for the apps that we build and the systems that we build to host those apps. And it gets really, really interesting. Some really concrete things. So I don't know if anybody's familiar with distributed hash tables. IPFS runs on a DHT, public or private. I'll touch on that a bit more. But a DHT allows you to do routing. So when you request data on IPFS, it works differently to move that request through the network and get to the data where it's hosted. This linked data concept, content or desk data, I'm going to dig more deeply into what that means. And verifiable peer-to-peer is core to IPFS. So not only allowing you to exist and move data across a network, but allowing you to connect with specific other peers on the network and actually have encrypted and verifiable communication of data with those peers. IPFS is actually a stack of different protocols, so a lot of people just talk about IPFS, but you can talk about some of the pieces internally independently, and they're worth Googling and digging more into. One of the core pieces of IPFS is a library called libp2p. So when they were building IPFS, they realized that networking, peer-to-peer networking on the internet is really hard. If you've ever done it, there's just a lot of work you have to do to things from discovery to NAT traversal is a really big challenge. And so they started building this library and realized, OK, we should actually pull that out and make that useful for a lot of other projects. And so you see libp2p, it's being used by Ethereum, for example, now. IPLD is this concept of the linked data. So if anybody's familiar with Merkle trees, it's the way that you can actually have structured linked data that connects folders and files online, as well as the bits within them, which is really cool. So I want to dig into a couple concepts just to get your brain firing on how this thing is working and what's neat and interesting and new about it. So content addressing. How do you get a file on the internet? So let's look at the way that we do it now. Normally, which is we call it location-based addressing. So you have some URL that you want to go get a file at, right? And that looks like this. So I want to go to this URL, and I want to get this file z.json. And so the first step is I'm going to take this full URL. I'm going to put it in my browser. I'm going to request it over a fetch request. Somebody's going to convert that URL to an IP address so that then it gets routed to a specific machine. That machine is then going to look at the path of the request and whatever other data, and then it's going to find that file wherever it's stored in a database, on disk, whatever. And then it's going to return it to you as the raw data. I just asked for ZJSON. I don't know if what I got was really the thing I'm requesting. I have some sort of trust relationship here with the server that's going to give it back to me. So So this breaks down. This breaks down a lot on the internet, and for a lot of different reasons. But you can imagine what I've mentioned a number of times, that at the bottom layer here, at the beginning of the journey, our network might disconnect. So the second that the Wi-Fi here stops talking outside to the internet service provider, we don't get any of these requests through anymore. The translation of domain name to IP address, that can break down. That can go away. Additionally, IP addresses are very correlated with geography, so it makes it very easy for governments to block entire ranges of IP addresses in order to block other countries and block traffic to those countries, which means your services aren't going to be available everywhere. That server could go away, or that file could actually just disappear. In the US, the Supreme Court, whenever they make a major decision, they write up an opinion about why that decision was made, usually by both sides of the opinion, the side that was of the majority and the side that was of the minority. And there was a study, I forget the exact number, so don't quote me on this, but there was a study that looked at URLs that were put into those decisions. These decisions are defining the law of the United States. And the URLs put in those decisions, it was something like, off the top of my head, it was like 70% of those links don't work anymore. So that's mostly towards those upper two. It's not that people are blocking them. It's not that you can't get the internet to get them, but it's that servers and files go away all the time. And so that data behind those links is really important, and I'm sure a lot of other people would have tried to help keep them up, but it's only left to the responsibility of that final point to do it. So in content-based addressing, this works totally differently. When you want to get z.json, what you actually have to do is you don't have to know the name of the file, although you probably know a bit of the metadata about the file you want. Instead, you have a hash. And so the way that you originally get the hash is the person who created z.json is going to use an algorithm to create the unique hash of that file. So you're probably at least familiar with hashes. SHA-256 is a really common one used in IPFS. And so SHA-256 is meant so that this z.file has an ID that is unique in the entire universe. There should never be another file created that has that same hash. And so now when I request that file from the IPFS network, everybody knows what I'm talking about. Even if they don't know what the file is, they know if they have it or they don't. And when I get that back from, from anybody on the IPFS network, I'll have some data, and I'll have the hash that I requested. And all I have to do is rehash the data to verify that I got what I asked for. And so that creates this really interesting setup where I can actually ask for the data behind this hash from anybody on the network without caring if I actually trust that they're going to give me back what I want, because I can always just check. And that's really powerful, and it allows us to think about building things in different ways, and it allows us to think about how we can take data that's really important for humanity and allow anybody to host it and make it available on the internet in a way that's not only replicable across the internet, but allows our applications to always be able to get it. And I'm going to talk a bit more about the always be able to get it in a second. Some of you might be thinking, okay, like that sounds really similar to why can't you just do the same with a CDN? Why couldn't I take that z.json with a CDN? That sort of misses the idea of the CDN could go away or the person paying for the CDN could go away. But it also misses the way that this is fundamentally different. And if you don't believe me, you should look at Cloudflare's work on IPFS and actually their experiments in making IPFS nodes and gateways available as part of their CDN, because they see this as like as a really interesting and alternative approach. And they're doing some really cool work there to try to figure that out. But this comes into play in reality too. So in Turkey. Well, let me start on Wikipedia. There's a page on state-sponsored terrorism, and there's all the classic actors in there. I mean, there's the United Kingdom, there's the United States, and there was Turkey, and there is Turkey. And Turkey didn't like that. They said that was actually lies from the media, and they have a law against the media lying, and they said, Wikipedia, you have to take that down. And Wikipedia said, we don't take things down, you change them, and if they're wrong, they'll be changed back. And Wikipedia didn't like that, or sorry, Turkey didn't like that, and so they did what I mentioned before, they blocked all of Wikipedia in Turkey. With IPFS, that's not possible because what you have to do, and there's a mirror of Wikipedia that is available on IPFS. So people that are thinking Wikipedia is one of those really valuable data sets for humanity, they put it on IPFS. So now when people request Wikipedia from an IPFS endpoint, they can ask anybody on IPFS. It isn't one IP address anymore that can be blocked. They can ask anybody on the network, and that can be routed through whatever number of steps it takes to get to somebody who has that data and will give it back to them. And so Turkey can't block this through IP addresses anymore. And it also lets us do things like these self-assembly networks. So now I can build apps like Werewolf. I could build apps like my healthcare app. I could build apps like a news app that can't be censored, or they'll work locally, or they enable peer-to-peer discovery. If you have an IPFS node running on your laptop right now, I could actually request data directly from it across this network. I mentioned before this concept of linked data. I'm just going to move a little quickly through this, but it's really cool. It lets you host not just files, but actually nested data. So this is through the command line, just adding a folder to IPFS. And you'll see at the bottom, the whole folder has a hash. And so I can request sort of all the data behind the folder, but every file within it also has a verifiable hash. But I don't necessarily even have to request those verifiable hashes. I can actually use the nesting. So this hash would actually have within the DAG like a / main.css. Every file itself has there's an algorithm that gets applied to it that breaks it up into a lot of small pieces. You can bring your own algorithm and choose how this is done. But that nesting is also really neat because I can ask for a file from the network, and anybody on the network can send me small packets of that file, and I can then reassemble the whole thing into the verifiable end file. So self-organizing, self-verified data, offline first, local first, which I think is really interesting to this community, and powerful data structures. So the nesting of data, and I'll show you just a little bit more of that as I finish up here. So now I wanted to move quickly here because I'm getting close on time about using IPFS with React, because that's where I want to kind of like inspire this crowd, because I think that React is just the perfect place to be pushing IPFS and doing some really cool things with a decentralized network of data and encrypted data ownership and offline first applications and self-hosted applications and peer-to-peer applications. And there's so much to be done, and so I want to bring you all in. So I just want to answer a few questions here. Can I use IPFS to host assets for an application or a website? So you just want some images in your app, and you want to be able to pull them into your view. It's really easy. Same way that I showed before, oftentimes adding data to IPFS is, you can do it through any language you want. But just on the command line here, I'm going to add a logo to IPFS. And then they have a JavaScript library if you go to js.ipfs.io. Later, retrieving that hash is as simple as doing an IPFS get. Now, I don't have to get that logo. I could actually get a whole directory, and this is that will be actually much faster. I can get the whole directory without getting necessarily traversing down and getting all the data. So then I can see what's in the directory and quickly go grab any hash for a file within the directory. And that's where this marriage with React is so exciting, because actually linking that with lazy loading and suspense, it actually gives this really powerful framework to do this in really clean ways and give really good user experiences behind it or on top of it. So yeah, but you can host your assets. If that's the simple thing you want to do, you can host assets on IPFS. It's easy. There's a million use cases of people doing that. But not only that, you can actually host entire applications on IPFS, and that gets really cool too. And you don't have to host applications on IPFS that are alternative to HTTP. So back to this example, I can take my home page and I can add the whole thing to IPFS. And then I can go to any IPFS node and actually request that root hash, and my home page will be there. Even more than that, there's a bridge between HTTP and IPFS. There are bridges all over the place, and there are some that are exposed in the browser. We call those gateways. So you can go to any gateway and actually load up your home page now by going to that hash. Okay, hashes, who wants to pass hashes around all the time? You want other ways to do this. So there's actually connections with your DNS providers. So you can actually use a tool called DNS Link to take your hash and turn it into your app, turn it into your web page URL. So then people can actually request your URL, and that URL will just go off to IPFS and get the data. Okay, so can I use IPFS for dynamic data? This is where it gets really exciting and interesting, because you don't want to be passing around the static hash of your app and having to change the hash every time you update it, or change the hash every time you change the state. And so dynamic data is totally possible, and it uses sort of the whole stack of technologies from IPFS to libp2p to IPLD. Okay, so your normal app setup, maybe you have your view, actions, and states. What we've been working on is how you can take your state or your store and connect it to a data structure that we call interplanetary event logs. If anybody's familiar with event logs, you should be able to kind of imagine what event logs do, but then we take event logs and we wrap them in a technology called threads, which you can imagine like a decentralized database that any app can pull from, or write or read to, or create new databases on the fly. This stuff is all, it's all using encryption, it's all private, so what happens is if there are two clients that are collaborating on a data set that need to be able to write, they exchange some key, and then they are able to both pull up that data set, create changes to the data set, and move forward. You can add new collaborators, whatever you want. So very, very like typical database approach here. I don't mean like a database manager. I mean like the core data structure. But so in the old version of Threads, it looked something like this. So there was a Notes app, for example. This was React Native, but it would you'd just in your app you'd list all the available threads, and then maybe you'd go to each thread and you'd fetch all the items within the thread. Or you would take a thread. Here I have some thread ID, and I want to store a note. And you can store any arbitrary data. It's JSON string. I think I was lazy in setting up the database schema here, and I was using Slate.js, so I didn't want to like figure out the whole schema of their JSON structure, so I just stringified it and was storing string blobs in threads. But then I can actually invite other people to my thread, and they can load it in their client, and it should synchronize peer-to-peer or use other nodes to relay that data between peers. So that gets really exciting. I don't know if people are very familiar here with CRDTs. So CRDTs is it's been gaining a lot of traction lately. A very exciting area called conflict-free replicated data types. And so if you think of something like Google Docs, where you have a lot of people collaborating on the data, what you want to do is make it so that anybody editing that file can get any other edits in any order, and they'll all still arrive at the same output. And this is a really interesting algorithm meets UX research area, and there's a lot of work building CRDTs. And so these threads and event logs are meant to be sort of an engine towards your CRDTs, if that's what you want. They can also be an engine for key value stores, if that's all you need. But they give you mutable databases over IPFS. They're private, peer-to-peer, or public. You can get multi-user, offline first, trustless, or anonymous. And so another really cool example here that it's more or less like a test of this, but you can see it online, takes a MobX-based app, connects it to interplanetary event logs, and then uses that whole stack. I haven't even talked about Filecoin, but that gets super exciting too. But so what it looks like any database you'd use normally. Here I create a model for a folder of files. Okay, so now I have this model, and that model becomes a thread. So every thread has some data type model that you define. And then when I want to add a file, I go ahead and create this file object that I've defined, and I push it. I push it to my on-device list, but I also save it in the thread that I've created. And then what's really cool, and this is where the synchronization gets interesting, is I can just listen to changes to this database, and anybody else that I've invited to this database can also make changes to it, and we can all be collaborating on this shared folder of data. And I can build my application to react to those changes in near real time. So this was supposed to animate, but you can go to the GitHub repos and check out how that works. So it's really exciting. It's very simple to start thinking about how to connect these things to your apps. There are some challenges still with IPFS. There's a really great blog post. It was written back in June, but by Tom McWright, and it's worth reading about some of the challenges of just building some simple things with IPFS. A lot of those are solvable, and a lot of them have been solved already and made easier already. But it's worth a read just to get your head around what you might face. It's moving fast. There's awesome things built on it. OpenBazaar, DTube, which is like a self-hosted YouTube with a shared index of all the videos. AnyType, which is like Notion. If anybody uses Notion, but this is local first. You own your data. They can never see any of it. It's all encrypted. Really beautiful application. And so I invite you all to check out these links and get started and figure out how to use IPFS in your next or current applications. And thank you very much.